Alright, today we are going to look at how we can find arc length using integrals. So, arc length is going to be equal to the integral of ds. Great! Now, how do we find ds? Well, ds, we have an equation for that. It's going to be equal to the square root of 1 plus dy dx squared. Now, sometimes if you have an equation, say in the form x equals blah 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 y, then you would use dx dy squared. But for our purposes, for our example today, our equation will be written in terms of x. So anyway, let us get a practice problem to work with. Say we have the arc given to us by y is equal to the natural log of secant x, right? All right, well, what do we need? We need dy dx, so let's take the derivative of this. And this is fairly simple if you know your natural log and trig derivatives. This is going to be equal to secant x times tangent x all over secant x. And our secants cancel each other out, so we're left with tangent x for our derivative. All right, now we can plug this into our equation for ds. ds is going to be equal to the square root of 1 plus tangent squared x. Remember, because tangent x is our derivative, and we want to square that by our equation. So, this looks rather difficult to integrate. However, if you know your pre-calculus trig identities, then you know that 1 plus tangent squared x is just equal to secant squared x. Super helpful in this case. And while we're at it, let's just take the square root of that. The square root of something squared is just itself. So we'll have that ds is equal to secant x. And we just made this so much simpler to solve. All we have to do is integrate ds. Now, if you don't know how to integrate ds, that will be a problem. But I know how to do it, so we're going to do it. The integral of secant x, and I forgot to give us some bounds to work with. So let's say we want to find the arc from 0 to pi over 4. There we go. So those will be our little bounds. We'll have 0 and pi over 4. Now, the integral of secant x, let me give that to you. This is going to be equal to the natural log of secant x plus tangent x. And if you don't believe me, I want you to take the derivative of this natural log right now, and you'll see you wind up back at secant x. Okay, so now we have to evaluate this at our points, pi over 4 and 0. Now let's think about this for a second, shall we? What is the secant of pi over 4? Here's how I like to think of it. Secant is just 1 over cosine, right? And I know the cosine of pi over 4 because I know my unit circle. That's going to be square root of 2 over 2. So 1 divided by the square root of 2 over 2 is just going to be equal to 2 over the square root of 2. So let's write this down. 2 over the square root of 2. There we go. That's what our secant of pi over 4 is. And now what's our tangent of pi over 4? Now we know what that is. That's just 1. That's a nice and easy one to do it for. Okay, and now we have to subtract our lower bound. So what is the secant of 0? Well, what is cosine of 0? That's right. Cosine of 0 is 1. So our secant of 0 is going to be 1. So let's write this. Minus the natural log of 1 plus, and then what is our tangent x of 0? What's tangent? Tangent is sine over cosine. Sine is going to be 0. Sine of 0 is 0. Cosine of 0 is 0. So we have our tangent x. Cosine of 0 is 1. Sorry about that. So tangent x is 0 over 1, which evaluates to just 0. And oh, we're running out of space here. Let's just plot this right here. This right side right here becomes ln of 1. Now, if you know anything about your natural logs, you know that the ln of 1 evaluates to simply 0. So all we're left with right here is this natural log. This right here is our answer. Now, we can get that radical right here. We can get that right out of the denominator if we want to. If you want to, you can. I'll leave that up to you. I don't really want to. So we'll just say that our answer for the length of our arc from 0 to pi over 2 is the natural log of 2 over the square root of 2 plus 1. If you made it to the end of this video, thank you for watching. I really appreciate it, and I hope you learned something.